Let's take a look at the fundamental theorem of algebra, and more important, its corollary. The fundamental theorem of algebra simply states that if we have some polynomial which has a degree that's greater than 0, so linear, quadratic, cubic, etc., we know that's going to have at least one root that lies in the set of complex numbers. Now remember, complex numbers are in the form a plus bi, so your root could be something like 2 plus 3i. If the real part is 0, your root could just be purely imaginary, so 3i. Or if your imaginary part was 0, your complex number would just be a real number, say like 2. So a lot of different opportunities here for what our root could be, but we kind of cover all our bases here by just saying it's a complex number. It'll ensure that it is in fact a complex number, an imaginary number, or some sort of real number. Now what this really means for us here is that as a follow-up or a corollary to this theorem is that we can say that every polynomial of degree n, so degree 1, 2, 3, whatever, can be factored into n linear factors that are also being multiplied by some constant in front. Now a lot of times that constant is just going to be 1, so we don't really notice it's there, but it is important to just acknowledge the fact that we could just kind of basically pull out a greatest common factor and leave it out in front. So we can see here, let's say we had like a 5th degree polynomial, we would have 5 linear factors lined up here of the form x minus our first root times x minus our second root times x minus our third root all the way down to x minus our 5th root. So these kind of are, with the subscripts, these are just our complex roots. Well, how is this going to be useful to us? Now, one main thing this is going to be useful for is that if we can figure out the roots of a polynomial, we can quickly come up with an example of a polynomial that would have those roots. So we kind of work backwards here. Also, if we know a little bit of information about some roots, we can find some information about some others. As we move along through this unit, we can see how to do some examples like that. Let's get started with that first example I mentioned. Let's say we know that a polynomial, maybe we got this from a graph, or just as just given information. We know that the roots of this polynomial were 3 and 4. Using that form that we just saw there from the corollary of the fundamental theorem of algebra, we know that this polynomial could have been written as the following factors: x minus our first root 3 times x minus our second root 4. So we've got our factors all lined up. We could have a constant out in front, but since I'm just asking for one particular polynomial, we'll just make sure it's 1. It'll make the calculations easier. And then we can just distribute out our two linear factors here, and we would get x squared minus 7x plus 12. And we can see that since we have two real roots to this equation, that if we were to actually graph this function, it would cross the x-axis twice. Now let's take a look at another example here. Let's say that the roots that we were given this time had kind of a mix match of different types of roots. So say one of them was -2, a real root. We had one root which was -i, and another root that was +i. Now remember that our complex roots, or our imaginary roots, have to come in conjugate pairs. So if we have something like -i, +i has to be a root as well. To kind of set this up, we'll go the same route here. We know that if these are our 3 roots, we can write our factored form of the polynomial as x minus our first factor times x minus our second factor times x minus our third factor. Now let's just kind of rewrite this so it looks a little bit nicer. We'll have x plus 2 times x plus I times x minus I. I would choose to distribute out these second 2 factors first, because that'll just be a little bit quicker, because they're a difference. Well, it's a sum and difference pattern, which will result in a difference of 2 squares. So we'll have x squared minus I squared. That can just be rewritten as x squared plus 1. And then we can just distribute out the x plus 2 times the x squared plus 1, and our final answer will be x cubed plus 2x squared plus x plus 2. This polynomial would have those same roots. We can see we have 2 complex roots. They come in conjugate pairs and 1 real root. So this would cross the x-axis once.